So we are actually now, after studying conduction and convection, we are ready almost to design a heat exchanger. So what happened in the heat exchanger design is one fluid is being cooled while the other one is being heated. That's the idea behind the heat exchanger. You are trying to send the joules or the PTU, we are trying to send them from one side to the other, right? And of course, it will always go from the hot to the cold. You cannot violate this. The temperature always, the energy always move from the hot to the cold, right? And so the easiest design is this double pipe design. Inner pipe, outer pipe, one fluid is going in the inner pipe while the other one is going into the outer pipe. The question is, should you make it in parallel flow or counter flow? Look at this. This is called counter flow. One guy is going this way, the other one is going that way. If you are the one who's making that decision, should you send the flow in parallel flow configuration or counter flow configuration? What is, so to answer that question, you have to ask yourself, what is the purpose of that heat exchanger? Like, how can you tell this is a good heat exchanger or this is a bad heat exchanger? It will be good if you do what? It will always exchange heat, by the way, right? And if it's really insulated from the outside, very well insulated, the 100 joule that the hot fluid, 100 joule per second, that the hot fluid will lose, the cold fluid will get them. No question, right? Those 100 leaving here will go there, assuming there is no losses from the outer shell. So parallel flow or counter flow, the energy leaving the hot will go to the cold. But what's really what do you think the ultimate criteria for this is an excellent heat exchanger? It will do what for you if it's really, really good?
It doesn't cost a lot.
Huh?
It doesn't cost a lot to run.
So the area should be smaller, correct? For the same Q, you want the area to be small. Jesse said that it shouldn't cost a lot. You don't want it to be really big. And that heat power plant in Jinx that we went to, those heat exchanger is as big as this room. You know, from this side to that side. So you want the area to be small for the same Q. Right? For the same Q, you would like the area to be small. Let's not call it H, right? I told you earlier today that it should actually be, does anyone remember? U. U is basically all of them together. Convection outside, convection inside, and conduction between them too. So yes, it should be a little bit smaller, right? So that's one thing. But also, what else you'd say this guy is excellent?
Efficiency.
So there is no efficiency assuming that there is no losses on the outside. It's all the Q leaving hot will go to the cold. It's not efficiency. It's something called effectiveness. And so to be this guy really, really very effective, what it would do, what do you think? Imagine this is, you're using this heat exchanger to cool the oil, the cooling water in your car. That's the radiator. The radiator is a heat exchanger.
The amount of time it takes to cool.
So you're saying that the Q should be really big for the same U and E. Right, of course, right? So Q should really be big, but I'm trying to point out to something in that drawing. So if we are trying to cool the water, cooling water in your engine, you would think your radiator is excellent if he managed to make the water as cold as the air. Right? If he managed to cool the hot fluid all the way down to the cooling medium, the air that's trying to cool the hot water, he would be excellent. Right? He did the maximum we can expect from him because he cannot do any more than this. So basically, if we can manage to bring this guy, the hot fluid, all the way down to this, temperature, the inlet. So if we can bring T hot all the way to T cold N, that would be best. Or if our purpose is actually to heat, some exchanger are designed to heat something, right? Like you have the air going into the, you're using the air to burn, for example, the coal. You have a furnace and you are using air to burn the coal so that you can basically get heat and heat whatever you want in the furnace. You would like to heat the air, right? And so some heat exchangers are used to actually preheat that air before you send it to the furnace. So if your job is actually to heat the cold fluid, the heat exchanger is designed to heat the cold fluid. The best heat exchanger performance would be to take this guy all the way to T hot N, right? So the heat exchanger, if it's for cooling, the best thing that they can do is to bring the hot fluid to the T cold N. And if it is, the purpose of it is to heat stuff, it will, the best you could imagine would be to bring T cold N all the way to T hot N. Right? So based on this discussion, which one do you like? The barrel or the counterflow? Right, because the barrel flow will never be able to do this. Right? The barrel flow, you are stuck with something in the middle between them. You will never be able to realize or achieve your dream. On top of that, there is something also bad about the barrel flow. Do you see any problem with this? Anything that you don't?
Really, really hot. You have to get the cold, really, really cold that you can just undo it.
That's what will happen when you are doing barrel. So Mueller is saying this: you have very cold fluid next to a very hot fluid. That's the nature of the barrel flow. Like you bring the cold and fluid from the same place. So the very hot fluid is next to the very, very cold fluid. And then they taking the journey together and eventually they meet in the middle. What is bad about this? Does any...
It slows down and it stops.
That's what I said earlier, like that basically they stop in the middle, they never really go, the cold will never get that hot and the hot will never get that cold. But from thermo 2 point of view, anything bad about this?
Is it the stress on the metal?
Right, but I'm a thermofluid, I'm not Dr. J. Hannon, I don't care about the material. From thermo point of view, what is bad about this? Thermo, not material science point of view. From thermo point of view, this is a waste of availability. This will increase the entropy of the system. This reduces the efficiency of the cycle. Anytime you use very hot fluid to heat very cold fluid and you have huge delta T between them, that make your cycle efficiency really drop. Right? That's why they have all those, remember the regenerative cycle, all those feed water heater you had in thermo 2? Why did they have all those guys? It's to prevent to basically try to send the water to the boiler at already very warm temperature rather than sending very cold water to the boiler. So you can see that barrel flow will end up shutting our ceiling for dreams. You know, we cannot really go that high, and it will result in very high reversibility, right? It will make our cycle efficiency really bad. So this is the best. We should aim for counterflow, right? As much as we can. Why as much as we can? Why we cannot always just go pure counterflow? Because it takes very long time to do this, right? It's a very long pass. So as a result, they would usually make it in, usually they are in shell. Let me show you. Usually something like this. So the tube are going, the one fluid is going through the tube while the other fluid is going on the shell. They call it shell and tube structure. All right? So it's not pure counterflow, but you can see they are trying to make it counterflow. How? The water that they are trying to heat, it's going in the tubes like this, while, let's make it actually blue since they are trying to heat. So that is the water that they are trying to heat, while the steam that they are using to actually heat this water, it's going like this. So you can see it's not totally counterflow, pure counterflow, but it's almost like counterflow, right? So Abad, if you are the engineer responsible for this and you end up saying, no, let's send the steam over here, that would be a mistake, right? If you do it like this, and you are sending the cold water also like this, that's parallel flow, right? That's more like a parallel flow. You will not be able to heat the water that much. Correct? All right. So for space limitation, they wouldn't do it really pure counterflow, although that's the best, but they will try to make it like in shell and tube, and they will try to make it like your radiator. So radiator is called cross flow. So the air is moving normal to the pipes. Okay? So that's a cross flow heat exchanger. So for all those problems, whether it's cross flow or whether it's shell and tube, what's our, and by the way, the shell and tube can also can have different configuration. It could actually have multiple paths of the tube and multiple paths of the shell. So for example, see, this is one shell, but the tube is going 4 times. So the tube can go 2 times or 4 times, or if in that sketch, ouch. In that sketch, the tube is actually just one pass, going one side, leaving the other. Right? And you can have 2 shells also. How you can have 2 shells? So after you finish the shell, there is another shell over here, where the steam will also go to the second shell. There are all those configuration. There is also, so this is a metal heat exchanger. So the hot air, and that's what they have in power plants. So the hot air leaving the furnace and about to go through the stack is basically sent over here. So that's the hot fluid. Let's actually make it red. So he would go like this, while the cold fluid, which is the air that we are going to use to burn our fuel, is basically going to the other side. And how does the heat transfer happen between the two of them? Mixing? What do you mean mixing? Like there is like leakage between the hot and the cold?
So it's pulling hot air into the cold air and cold air into the hot air.
It's more than this. So Jesse is saying that as this thing rotates, it actually take hot air and send it into the cold air side. No, this is actually a byproduct. That's not the main mechanism for heating. The main mechanism is, right, the plate gets soaked in the hot fluid for a long time, so this thing is rotating very slowly. So it gets soaked, become red hot, not red hot, but really hot, and then it passes to the other side, where it gets cooled by the fluid. Right? So that's the air preheater they have to heat the air before it goes to the furnace. And that's another picture of the shell and tube structure. Right. He's actually pointing out to the fact that sometimes you are also using it to try to make the steam vent the air inside it. Sometimes the air would go into the steam and you would use it as the aerator, meaning you basically let the air accumulate on the top and you just vent it to leave the cycle. I'll show you a better picture later. Right? And so those are the small boilers that you would find in hotels and hospitals. So the furnace over here sending all those hot gases inside the pipe. So the pipe have the very hot gases, while the water is sitting on the outside. So it's like as if you are making tea in a kettle, right? So the water would boil along those on the outside, right? And just make steam. So that's a heat exchanger where one side it's completely filled with water and the other side, those are the hot gases moving into the pipe. And this is the large power plant that I was telling you about. So you can, the boiler itself is like really a heat exchanger where the hot gases are moving in the middle and the wall of the boiler, this 10th floor boiler, all the wall are covered by water pipes. So the wall is out of water pipes and the water basically having or looking or in contact with the hot gas in the middle, they make the water boil inside there. So at the end, you'll end up getting steam out on the top of the pipes, right? And by the way, those boilers, they actually hang them from the top. They are not standing on their feet. The boiler is actually sitting from the top because that's my question. Why they don't want it to be in contact with the ground? No, it's not heat transfer problem. It is Mallory's thinking that, well, the boiler, and she's right, the boiler will probably be hot and you don't want to conduct to the floor, but you're conducting from the top because you're hanging it from with metal springs too. Why do you think they hang it from the top?
Potential energy, gravity.
Huh?
Gravity and potential energy of getting it back down to the.
No, it's not gravity. It's because when they start the operation, it gets very hot, it expands. And so if it's sitting on the floor and expands, it can pull from its frame. But if they are hanging it, it can actually, and so it's like, they say it's like 1 feet between when it's full. And also the water, when you fill it with water, it also expands a little bit. So they make this joke that one day one of the workers actually put his toolbox under when they were doing the maintenance. When he turned on, he couldn't get his toolbox. And they told him you have to wait for 6 months because that's when we turned off again.
The first people to make the mistake of putting it at the bottom.
Right.
Same thing.
All right. So the essence of that process between the fluid, the cold fluid and the hot fluid is convection, conduction, and convection. Right? And that's the part when I say that R is the 3 R's. H in the inside, R conduction, and H on the outside. And we will pull all those guys together by 1 over UA. So 1 over UA is 1 over HI plus R wall plus 1 over H out, area out. This 1 over UA, you should wonder what area, because if we base it on the outside area, or area out, you will get one number. If you base on the inside area, you'll get another number. And that's correct. So when someone tell you the overall heat transfer coefficient, you should ask based on what area? The outer area or the inner area? All right? And this is when we say usually the conduction is really tiny compared to the convection on the inside and outside. So we basically just say R is 0. Right? And if the area, if the pipe thickness is really small compared to its diameter, then area N is the same as area out. It's just basically just area. And that make those 3 guys just one number, the overall heat transfer coefficient. Right? But you should check when you are given the U, when you are giving the overall heat transfer coefficient, you should check what area was it based on. Okay? And if one of the surface area is actually fanned, and so that would be the case when you have small H, like for example it's air, like for example your radiator. So you are cooling one side with air, the other side is the hot fluid. So that side with the air, we know the H air is not really that great. So what do? They add more area. So at the end of the day, HA need to be big. So either you push the H really high or you make the area really high. And so they make the area really high by adding the fans. But we know that that area, that the new area, that new area total shouldn't be used in this equation. When you say Q is H area, you shouldn't use delta T, you shouldn't use all the area, because the area fend is not as effective. Excellent. There is an efficiency associated with it. It's area fend multiplied by efficiency fend. Okay, so if the pipe is such that there are certain area that's not fend, you use this area. But the area fend, you cannot use all of it. You just have to multiply it by efficiency. And that efficiency will come from the boundary condition. Is it insulated at the tip? Is it very long? You know, we have 4 efficiency for 4 different boundary conditions. Right? Right, and so those are the typical number that you should expect for you. So that overall heat transfer coefficient, and those are the type of heat exchanger that you would actually see in practice. So water to water, you should expect a U of between around, say, 800 to 1700. Water to oil, you basically see gas to gas, and look at this. So gas to gas, you see this? So that tells us why we put fins on the gas side, because the H is usually very small when it comes to the air. But when it's fluid, when it's water, look at the U is almost H, right? It's not H, it's 1 over U is 1 over H plus 1 over H. But it's mainly the H's that's doing that U. So that basically tells us that the H for the water is much, or liquid is much higher than the gas, and that's why we need the boost from the area. And finally, we'll finish the last minute by saying that if the pipe wall has a lot of dirts and deposits because you are, say, ash, you are burning coal, and this pipe is now completely black from the outside, and the water that you are using on the inside, ouch, ouch. So you have ash on the outside and you have falling on the inside. That basically add 2 extra resistance, right? It's basically as if the wall has another wall on the inside and another wall on the outside. So you have 3 conduction. And because they are in series, it's R plus R plus R. And those are the typical resistance that you get from those fluids. And we are done. Thank you.